So today we're going to talk about the structure of ionic solids. So here's a 3D image of a lattice of an ionic compound. You can tell that this is probably an ionic compound that has a 1-to-1 ratio, something like sodium chloride, where you have one sodium ion for every one chloride ion. It would be a slightly different structure if you had something like calcium chloride, where you have one calcium ion for every 2 chloride ions. You'd see a slightly different structure. Now, you won't ever be asked to draw in 3D like this, but you could be asked to look at diagrams or draw simplified diagrams. So a simplified diagram for sodium chloride would be something like this. And then the positive ones and the negative ones, forming that lattice, that alternating lattice structure. So that would be for a solid when it forms that rigid, organized structure. And we're going to look at what it would look like when it starts to turn into a liquid or if it's dissolved. So here is another depiction of a lattice. This one is specifically sodium chloride. So this is as a solid, and you can see that rigid structure in 3 dimensions. Everything's held together. But if it melts and becomes a liquid, it breaks some of those bonds, all right, some of those ionic bonds. And so it loses that rigid structure. But it still has some attachments. Otherwise, it would be a gas. So it still has some of those bonds, but they're just not that rigid structure anymore. And the energy it requires to break down that lattice is called lattice energy, and it is dependent on Coulomb's law, which we talked about in the last section. So it's dependent on 2 things, the size of the charge and the distance between the ions. So that's why you'll see a difference between something like sodium chloride and lithium chloride. Lithium has a smaller radius than sodium. So lithium chloride will have stronger attractions because of that decreased distance. And so it will take more energy to melt it than it will for sodium chloride. Now, ionic compounds are typically soluble in water, and that's because of the alternating ions and because water is polar. So water has oxygen and hydrogen, making oxygen slightly negative and hydrogen slightly positive. So because of that, if you have a negative ion like chloride, it can form attractions with the positive end of the water molecule. The sodium ions could form attractions with the negative end of the water molecule, and that allows it to dissolve. So this is a nice image of sodium chloride dissolving and being surrounded by those water molecules, and you can see each of the ions is separated now, which allows it to conduct electricity as well because it has those separate ions. Okay, so our example here, why does KBr have a higher lattice energy than Ki? So our potassium is the same, so that means we just need to compare bromine and iodine. Bromine has a smaller radius than iodine, okay? So because bromine has a smaller radius, it has a shorter distance between the potassium ions and the bromine ions. That distance is smaller than the distance between potassium and iodine. And of course, according to Coulomb's law, the smaller the distance, the stronger the Coulombic attractions, leading to KBr having the higher lattice energy.